on static equilibrium. This is Dr. Butler and this is AP Physics. So, in this example, or in this lesson, I just want to look at what static equilibrium is and then how you would solve a problem using the concept of static equilibrium. The most important thing about static equilibrium is that there's two concepts. In static means it's not moving. Equilibrium means that everything is balanced. In order for that to happen in a rigid system, there has to be no net force. And we already have talked about that. We express that with the sum sign. There is, and force, all the sum of the forces is zero. That is what we already know. Also, then now we're going to add a second concept, which is there's no net torque. And we'll look at those two equations together to see that. So it is an important, if we were to build bridges in this class, this would be the main concept that you would want to understand for bridges. But any structure that is not moving uses this concept of static equilibrium. You have to think about the forces, but you also have to think about the torques. So total equilibrium, no net force, no net torque at any point on that. Otherwise, it's going to collapse and fall. Okay. So now, if you were to solve a problem with static equilibrium, these are the things you have to do. First of all, you would take a diagram of your structure, and then you would have to draw all the forces acting on it. So if we're looking at, if our structure is this plank that is in between two support points, what forces are acting on it? Well, there's the upward force of the structure of support point 1. There is an upward force of support point 2. And then there is the downward force of gravity. And it is being applied at the center of mass of the object. Okay? So in order for this to be in static equilibrium, two things have to happen. The net force has to be 0. So this is an equation. I would write that equation down in your formula packet. You should understand what that is at static equilibrium. And so the forces, you have to look at all of the x forces, and then you have to look at all of the y forces. In this problem, the x forces are not that important. It's more about the y forces. So you have your up force is normal 1, your other up force is normal 2, and your down force is your gravity force. All of those, if you consider their signs, have to add up to 0. And then the second part of static equilibrium is that the net torque equals 0. So now torque, you have to define a pivot point. Now the pivot point can be any point you want to define. All right. I am going to define the pivot point in this question right at support point 1. That's my pivot point. Actually, I'm going to do that in a different color. So my pivot point is going to be, that's what everything is going to rotate. Is it going to rotate up? Is it going to rotate down? If it's in static equilibrium, all of the rotating up forces, torques, and the rotating down torques are going to be 0. All right, so in order for this to be that. So in the forces, you're only looking at the upward forces and downward forces or side-to-side forces. In torques, you're looking at the rotation. About this pivot point, the normal force from point 1 is not affecting the rotation at all. So you ignore that in terms of torque. And then if you look at that in the other ones, there is a pivot point. So the lever arm for gravity is from here to here, which is going to be half the length of that, and it's going to be torquing it in the clockwise direction. So we're going to get a negative torque out of gravity. But the normal force on the other side is also going to be torquing it, and it's going to be torquing it upwards. And so we are going to get a positive torque on this. If this thing is truly in static equilibrium, the negative torque and the positive torque are going to cancel each other out. All right, so that's what static equilibrium. If the torques are not balanced or if the forces are not balanced, then this thing is not going to be in equilibrium. All right, so an example of a problem here. Will the ladder slip? Here's a ladder. It's 3 meters long. It's against the wall at an angle of 60 degrees. The minimum value, we have to figure out what is the coefficient of friction on the floor. So we're looking down here in order for the ladder not to slip. Okay, we are going to ignore, there's no friction on the wall. We're going to ignore the friction on the wall, but we're only going to be looking at friction down here at the bottom. And so we have to look at all the forces that are acting on this thing and then look at the torques that are acting on it. And so you can see kind of how this has already been somewhat set up for you. So this is our question mark is, what is the coefficient of friction on this thing? So I have it set up right here. And you could come up with 4 forces acting on the ladder. There is gravity force, of course, which is pulling it down. There is a normal force from the ground, which is pushing it up. There is the friction force, which is preventing it from slipping. And then there is the normal force at the top of the wall pushing against the ladder at the top. All right, so we have to set up all of these equations to be able to make this there. And I'm going to use text to type this out here so that it doesn't. So the first thing is we want to look at the x forces on this. And we want all of the x forces to equal 0. So what are the x for it to be in static equilibrium? Well, we have in the x direction, we have our normal 2 force. I'm going to use capital N, and which is going in the positive direction. And we have our friction force, static friction force, which is going in the negative direction, and those have to be equal to 0. In order for this to be in static equilibrium, that has to be true. We also have our y forces have to be equal to 0. So in this case, we have our y forces. We have the downward force of gravity and the upward force of, so we have the normal force on 1 minus the gravity force has to equal 0. So those are 2 things that we already have set up. Let me put in for some of these. We can we don't know what the normal force is at the top of the ladder, but we do know what friction force is. So normal force minus the friction force is mu. I'm going to use a u for mu just because I can do that. Times, it's the fun equation, times the normal force. Times normal of 1. That's going to be the coefficient of friction. That's going to be our friction force equal there. And that has to be equal to 0. All right, and then if I solve for this one a little bit, our normal force of 1, we don't necessarily know, well, normal force of 1 and the force of gravity, so normal force of 1 minus the force of gravity, which is mg, must equal 0. And that actually tells us that our normal force is equal to our mg. All right, so those are the sum of the torque, some of the forces that are on this object. Next, we would need to also add our torque ones. And on this one, I cannot write. So we're going to use the sum of the torques have to equal 0. Okay, so now what are our torques? Go back to our... So what are our torques? We have to define a pivot point. Now the pivot point is very important to define because whatever you put the pivot point on is not going to be able to give you any torque. We could put our pivot point at the bottom right here because then we have the friction force and the normal force are going to provide no torque around that pivot point. but we could put the pivot point in the middle, or we could put pivot point at the top. I am recognizing that N2 really does not play a part in the equation. So I am going to say that our pivot point should be right up here at the top. So if it's pivoting around there, we cannot have any slippage around any of that. All right, so defining all the torques, then we have our gravity torque, which is going to be in the negative direction. I'm just going to work down from this way. So we have our Fg, which is mass times gravity, times the angle that it is on, that the angle next to the y, next to the lever arm. So what is this angle right here? Well, we know that this angle is 60 down here. This angle is not going to be the 60 angle, but we have a right triangle. We could kind of draw a little right triangle here. This is our 60, so that angle has to be 30 right there. Often in these kind of questions, figuring out what is, so we want mg times the sine of 30 degrees is going to be the torque from Fg. Okay, and it's in the negative direction because it's counterclockwise. Now we have these two forces at the end, times the lever arm, which is L over 2. Okay. Now over here we have the normal force is going to be providing a positive torque. So our normal force, which is mg. And this time mg is, what is the angle of this? And we have a little bit of an angle right here. And that is going to be 30 degrees right there. So we have another 30 degrees from the N1, but it's at the end of the thing. So it's going to somewhat cancel the other one, but not quite. Okay, and then we have one more torque. I'm going to move this down here, which is the friction force, which is now going in the opposite direction. I mean, it's a negative torque because it's rotating it counterclockwise. It is at an angle of 60 with the lever arm. And so we have our friction force times, so force times the sine of 60 degrees times our lever arm, which is L. And that all has to equal 0. Okay. I'm going to simplify this a little bit. I see these first two terms can kind of add up. So we have a negative blah, 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 L over 2, and we have a positive blah, 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 L. So that is going to give us a 1/2 mg sine of 30 times L. I'm going to put little times in here. We can maybe see that more clearly. And then this last one, we can also add the friction force, which we already have figured out is your mu times the normal force, which is mg, times the sine of 60 degrees times L, and that's going to all equal 0, and we can start to solve these. So what we need to do is we need to solve for our coefficient of friction. That's what we're going to do. One of these equations we're not going to use because it doesn't help us right now because we don't know what N2 is. So I'm not going to use that equation. So we have our normal force and we have our this. And we have actually plugged in some of those things and our torque force that we can use. And then we can solve all of this stuff. So I'm going to solve for mu. So mu times mg times the sine of 60 degrees times L is going to equal, and I'm just manipulating the equation up there, 1/2 of m times g times the sine of 30 degrees times L. Nice thing is we can do a lot of little canceling out here, and that often happens in here. We can cancel out the m's, we can cancel out the g's, we can cancel out the l's, And we're going to be left with just some signs and all of that. So our coefficient of friction is equal to 1/2 of the sine of 30 divided by the sine of 60. And we can plug those numbers in there and get a value. Make sure you're using the right mode, whether it's radians or degrees. We're going to be using degrees because of this. So the sine of 30 divided by the sine of 60 divided by 2. And we get a value of 0.288. So our friction force, our coefficient of friction has to be, so we need to make this an equality right here. If it is bigger than this, it won't slip. If it's smaller than that, so it has to be greater than or equal to 0.288, and that is the answer to this question. So that is static equilibrium. In class, we will discuss this a little bit more, but I wanted you to see this as a little bit longer problem so that you can try to solve it. Thank you.